Hi, I'm Alex, and I will talk about physics of Star Trek. As a longtime fan of science fiction, I always wondered how far are we from that future? Star Trek itself is a utopian society populated with multiple sentient species. They can travel faster than light, they have phasers, matter transporters, and to make things interesting, a bit of genetical engineering. Since this is a physics discussion, I will start with FTL travel. Story about a group of people that travels around the galaxy and has adventures every week at a different location has to have some kind of faster than light travel if writers wish to have a different adventure every week and keep science in the genre name. And that's because theory of relativity imposes ultimate speed limit in the universe. Remember this guy, Albert Einstein. He's behind the theory of relativity. Anyway, nothing in our universe can travel faster than light, and even light has a speed limit 300 million meters per second. Seems large, isn't it? Especially when we, today, even with the fastest machines we have on Earth, a space rocket, can barely reach the velocities that cover first 5 digits. But universe is big. It takes around 4 years for light from our Sun to reach its closest star, Proxima Centauri. For a space shuttle, it would take 165,000 years. A breakthrough starshot relies on the most advanced technologies today to reach 20% of the speed of light, and that nanocraft would be able to reach Proxima Centauri in 20 years. So, why not go faster? Again, theory of relativity presents us with a problem. Closer we get to the speed of light, our length shortens, mass increases, and our time goes slower. Here is a photo of me taken in a state of rest. In a physical sense, as you can see, I was not resting. And here it is how I might look like if the same photo was taken while I was traveling near speed of light. But even if we ignore the obvious squishiness, the real trouble is increase in mass. See, this increase in mass means we need more energy to accelerate the same object just for 1 more meter per second when we are close to the speed of light, compared with the energy requirements at the beginning of the acceleration. And that causes significant obstacle for us. Star Trek introduced a rich energy source to power its warp drive, matter-antimatter interactions. I will explain the energy source in the next video. Now let us concentrate on the idea of the warp drive itself. Thanks to the theory of relativity, warp drive might be possible. In this concept, the ship uses lots of energy to curve the space in front of itself. In essence, it squishes the distance in front of itself, traveling through shortcut without need to go over the speed of light. This is possible because of this equation that connects mass and energy. The reason behind this space deformation comes from the idea that gravity is a consequence of the space-time curvature, and mass is causing space deformation. This hypothesis is proven by gravitational lensing, bending the light when it passes near massive objects. You can see here a light from the far galaxy bended around the star. This is a Hubble image. Anyway, each massive object distorts spacetime continuum around itself, and failing or orbiting objects are actually following the straight line trajectories. Just like our straight line traveling on top of the Earth is actually traveling along its circumference, a very non-straight line. But newly discovered gravitational waves put question mark on gravity as a consequence of the space-time curvature. See, there are two major explanations of gravity, one offered by Einstein containing the curvatures, and other offered by particle physics. The second one sees gravity as a force, predicting a particle that will transfer that force, just like a photon transfers electromagnetic force. Discovery of the gravitational wave indicates that there is such particle and leave us wondering, can space-time be curved at all? The answer is Yes, it can. Answer lies in the encompassing M theory, where M stands for mother, the theory that provides a framework for unification of quantum mechanics and theory of relativity. The particularity of this theory is rather large number of dimensions, and as a curiosity, this image sort of shows you how objects could look like in such multiple dimensions. This is a cross-section of Calabi-Yau manifold.